Using our understanding of intermolecular forces, we can start to then explain and predict the properties of molecular compounds and their interactions with each other, because a lot of biological systems rely on the interaction of covalent compounds or organic molecular compounds. One common property is vapor pressure. We use this in a lot of medical instruments, and so it's good to understand how this works. First, what is this vapor pressure? Well, vapor is the transition, or it is a gas. So it is the compounds that are in liquid form escaping into their gaseous state. All right, and so as they move into their gaseous state, they're going to start to exert a pressure on the system around them. So vapor pressure is the escaping tendency of the molecules within that system. If you have a closed container, the vapor or those gas molecules will accumulate and they're going to start to push pressure on the liquid surface. Here in this diagram, this is kind of like how a mercury thermometer works or barometers, something along those lines. So that gas is going to exert a pressure onto this liquid in this tube. Oh, this thermometers as well. And at some point, it's going to exert just enough pressure that the pressure of the mercury or ethanol, what happens to be there, is going to be equal, and we can get what that vapor pressure we can measure it is. But as you change properties, you can change how much pressure there is on the surface of the liquid versus the atmosphere surrounding. When those molecules interact with the surface, they're going to condense and they're going to go back into a liquid state. And then we're going to have that liquid go back into a gaseous state. And at some point, you're going to have that equilibrium so that you're going to have the rate of the change from a liquid to a gas and gas to a liquid is equal, and that's when we know we can measure our vapor pressure. Factors that affect vapor pressure. A lot of it comes down to what are the intermolecular forces that are interacting between the molecules of the substance that we are looking at. The stronger the force, so going from dispersion to dipole-dipole or ion dipole to hydrogen bonding, you're going to have less vapor pressure because there's going to be less particles that can escape the liquid state to the gaseous state. So when you have a liquid, remember you have more interactions that are occurring as they're flowing past each other. In a gas, you've broken all of those interactions, and then you're going to decrease or minimize what's happening there. So if you have stronger forces, it takes more energy to pull those molecules apart from their liquid to their gaseous state. Temperature can affect vapor pressure. So as your temperature increases, so if we look at this first image, you can see the rate of vaporization to condensation is low and we have our pressure. But if we're going to heat up this system, you're going to have a lot more vapor forming and you can see the pressure goes up. This is kind of like if you take a disposable water bottle, so it has that crinkly plastic. So you drink some water, so there's some air left on top. You put it in the fridge and the bottle is going to be like collapsed, squishy, crinkly, because there's more liquid than gas, so you've decreased the amount of vapor that is up in that empty area. But if you take that bottle and put it somewhere warm, like a hot car, that bottle is going to expand because it's trying to force more gas or more of that water into its gaseous state, causing the pressure within that bottle to increase, and we can see that by that bottle expanding. Atmospheric pressure also plays a role, especially if it's in an open system. So I was just talking about a closed system. So an open system, like boiling a pot of water, you have atmospheric pressure pushing down on the surface of that water. And as we input the energy into that water, what boiling point is once the water's kinetic energy breaks the atmospheric pressure pushing down, it can then allow the water to escape into steam or that vapor. So boiling point occurs when you are able to break that external atmospheric pressure. depending on the strength of those intermolecular forces. So here we have diethyl ether, so that's just going to have dipole-dipole. Based off the atmospheric pressure, it's going to take less energy to reach that boiling point because of those interactions it's a lot easier to break those apart. Ethyl alcohol, which has hydrogen bonding, has a higher boiling point. So it takes a little bit more energy to break the interactions between those ethanol particles, those ethyl alcohol molecules, and then they will then overcome that atmospheric pressure. And water, by far, out of the simplest molecules, does have the highest because it has the most exposure to hydrogen bonding. It has 3 to 4 hydrogen bonding sites with 2 lone electron pairs and 2 hydrogens. When you have less atmospheric pressure, so like higher altitudes, like here in Colorado, you're also going to see a lower boiling point because we have less atmosphere that we have to overcome. So water here in Colorado actually boils at 93 degrees Celsius instead of the 100 degrees Celsius. So it actually takes longer to cook pastas and stuff like that because the temperature is lower. So all of this takes into account if you have an open system or a closed system, what is the temperature and what is the interaction between the molecules that we are looking at. Another property is viscosity. So viscosity is the measure of a fluid's resistance to flow, like how easy can it flow. We look at water as the base compound we look at. So we kind of said like this is water is 1. Are you more or less viscous than water? As you change the intermolecular forces, you're going to change the velocity, or viscosity, sorry. So if you have very weak intermolecular forces, it's going to flow a lot easier. It's going to spread out. If you've ever spilled like acetone, it just kind of spreads out. It doesn't bubble up or anything like that because it has a low viscosity. Water, if you've ever put water down, it bubbles up because it's got a higher viscosity. And then if you've had like honey or molasses or something like that, it's got even higher because it's got a lot more intermolecular forces due to the size of those compounds, right? So here looking at oil, the different types of oil, we can predict based off where this ball is falling, what is the viscosity of this liquid. The further that ball travels, the more or the less viscous it is, and then if it doesn't travel as far, the more viscous. And so this is important for cooking, oil, fractional distillation of making from crude oil to our gasoline and kerosene and stuff like that, but also looking at the temperatures and the interactions of the body, right? What is the fluid inside the cell? What's the viscosity of that to allow metabolic processes to occur? Our plasma, blood, so on and so forth. So having an understanding how molecules move and flow is a very important concept when we're looking at interactions of molecules. The last property we're going to be looking at is surface tension, which is the resistance for that liquid to spread out. And so we mentioned this with viscosity. What we are looking at is the interactions that are on the surface of the substance and not interior, because interior has 360 degrees of interactions. We know that. But on the surface, you only have your neighboring molecules and maybe those that are beneath you. If those are strong enough, they're going to hold together and form like this water droplet. So as we mentioned, with acetone, its interactions are weak. So when you drop acetone down on a table, it's going to spread out. So it's got very little surface tension, very little attraction to each other, whereas water has high amounts of surface tension, so a high amount of strong interactions, so they don't break as easily. And so like what a water strider, when it's interacting with the surface of the water, its weight is just distributed enough to not break the surface tension, so it can stand on top of the water. But if you put too much pressure, too much weight, or downward force on a smaller surface area, the surface tension can break and then you sink or whatever it happens to be.